Hello, this is Jacob Martin, working with an observational astrophysics group this summer, along with my mentor Lana Henry and my faculty advisor Crystal Martin. So my research project is about a epoch in the history of the universe known as reionization. This occurred about 12.7 billion years ago, as you can see from this chart, which outlines the big history of the universe according to the Big Bang Theory. Epoch of reionization was marked by the formation of the first stars and galaxies, and it's called the epoch of reionization because that's when all the neutral hydrogen in the universe became ionized for the first time after the Big Bang cooled. So the goal of my research project is to determine how the hydrogen gas between galaxies, called the intergalactic medium, became ionized. We suspect that it was ionized by high-energy ultraviolet radiation emitted from galaxies formed at that time. But due to the extremely faint nature of these galaxies, it's hard to make observations to confirm this. So what my group did before I joined for the summer is they used a technique known as a spectrographic sky survey, in which they looked not for the continuum radiation as a kind of a normal imaging survey would, like you would see from Hubble or something, but looked instead for a sharp spike in the continuum emission. And so spectrographic surveys, however, do have a few disadvantages. One is that they can't cover a very large portion of the sky at once, and the other is that they're interfered with heavily by emissions from our atmosphere. So in order to counteract this, at least the second effect, my group chose a window of wavelengths without too much atmosphere emission. Here's this is the spectrum of the night sky. And there's a gap here due to the quantum mechanics of how molecules in the atmosphere emit light. This is all OH or hydroxyl emission. So then to solve the other problem, my group made a slit mask like this so they could view the spectra of a large portion of the sky at once. And here is the kind of raw data out. So all these little black dots are emission lines they found. And then once you find a line, you have to verify that it is indeed a galaxy. And there are kind of two ways you can do that. You can look at the spectrum more carefully, go back and look at it more carefully and see if it fits the profile of what the line we want from our galaxy looks like. They actually found some other closer galaxies, and that's what my partner Joey Vaughn's project is about. And so, and then the other way is you can look at imaging of the area, and if the galaxy is resolved, you can identify it because it cuts off shortward of a certain wavelength, and this is where the ionizing radiation is absorbed by neutral hydrogen. Alright, so what's my job? My job specifically is to measure a parameter known as beta, and what beta does is it indirectly tells us how much ionizing radiation these galaxies are putting off, how much is escaping from their interstellar media. And so here, if we graph luminosity versus wavelength on a log scale, beta is just the slope of the kind of continuum profile here, right before this cutoff, where I said before that we can no longer see the radiation. And so, as you can see here, the steeper the slope of beta, the more ionizing radiation is put out after the cutoff. Alright, so the first approach that I tried to measure beta is I looked for our sample of galaxies in previously existing image catalogs. So, because when astronomers like to use the same patches of sky over and over again, just because there's lots of legacy data already. But unfortunately, all our galaxies were too faint to be definitely identified, and so now I have moved on to looking back at those spectra, which we originally analyzed to determine that our galaxies were indeed the galaxies we wanted to look at. And so what I'm doing is I'm looking I'm looking at the noise in those spectra and seeing if I can kind of take an average and see an average continua from our galaxy. So each individual spectra doesn't have any continua visible, but if you take an average, sometimes you can see kind of a trend, and from that we can measure beta. Fortunately, I haven't done this yet. I'm doing this very soon, but kind of the first step to do it is you take these lines and you have to get them into the same rest frame. To do that, you kind of fit them. This is just a example fit. The profile and fit later will be different, but you want to find where the center of the line is, because this will tell you the redshift, and the redshift is also related to the actual resolution of the lines. You have to change the resolution to get all your lines into the same rest frame before you can stack and then measure beta. You might see some of these things off here. These are just kind of remnants of skylines that were subtracted from the spectrum. Alright, so once we do get beta, what it will mean? Well, basically it will be used as a constraint for cosmologists who want to create models of dynamics from the epoch reionization. So beta is controlled by a few factors: age, metallicity, and dust. So the younger, the less metals, and for an astronomer, so you know, metals is anything past helium. Or as you don't know, and then dust from nebula. So the most important part of what we wanted, what we're thinking about most is the nebula contribution to these continua. So as you can see here, even if you have, this is a figure from a different paper, which claimed to have measured very blue beta, but has since been disputed. But they made this graph which shows that even if you have kind of a very low metallicity and young galaxy, the nebular contribution will still cause beta to not reach kind of a very blue value, or very steep, we call it steeper value of betas are blue. And so what that means, what they argue, is that there has to be some sort of mechanism by which the nebula are escaping from the galaxies, allowing the ionizing radiation to get out and causing what we view here. So hopefully after we measure this, we can then, it'll be kind of something that a lot of people will want to look at and try to interpret. And so I'd like to thank my advisor, Crystal Martin, my mentor, Elena Henry, Erica Lubin, who runs the UC Leads program, and then UCSB, and then National Science Foundation, David and Lucille Packard Foundation, and NASA for funding my research group. Thank you.